Okay, we're going to start talking about more basic derivative rules, a little bit more of an application type of deal going on for this set of notes. Just kind of understanding what a derivative is and stuff around it. So our first example, let's sketch a graph of a function such that the derivative is less than 0 for all of x and the rate of change is increasing. So this means that f is decreasing. So when I sketch my function here, I'm going to sketch a function that is always decreasing. Now I can't just sketch any decreasing function. It says that my rate of change is actually increasing. So what does that mean? That my rate of change is increasing. So the derivative of the derivative is increasing, which means that instead of getting steeper as my decreasing function, it's actually going to start to level out at 0. And I'll just draw it and I'll explain it here. So this is decreasing, but then my rate of change is actually increasing. And there's my example. The reason this works is this is decreasing the entire time, but you notice that my slopes are all getting more and more positive. They don't get positive, but they're getting more and more positive. So like, for instance, this slope might be like a -2. This slope might be a -1. So it is increasing. It's still negative, but it's increasing. And this slope might be like a -1/2. So this is a graph that fits that description. Okay. Let's talk about another piecewise function here. Let's find a and b so that f is differentiable everywhere. And whenever we say differentiable, there's that little hidden word there of, and it's continuous. So if it's differentiable, you can find the derivative at every single point, and it's also continuous by definition. So what I'm going to do first for this problem is I'm going to look at make sure this is continuous at 2. This is a piecewise function, so when I plug in a 2, these two should be equal. So I'm going to go ahead and plug in a 2 right now. And a times 2 squared plus 1 should equal, when I plug in a 2 right here, b times 2 minus 3. Let's clean this up, make it look nicer. 4a plus 1 equals 2b minus 3. Now, I'm going to end up having a systems equations here, so I'm going to just want to throw some of the stuff on the other side. So I get 4a minus 2b equals -4. All right, next part. I'm going to do this part in red for the differentiable. If I were to find the derivative of this, I would get 2ax plus 0. Because derivative of 1 is 0. And that's when x is less than or equal to 2. And the derivative of the bottom is going to be just b. And that's going to be at x is greater than 2. Okay. Now, when I take this, I have to set these two equal to each other when I plug in a 2. So when I plug in a 2, I'm going to get 2 times a times 2. And that's going to equal b. So I'm going to get 4a equals b. So a couple different ways to solve this. You can go ahead and set this up like this. I think it's set up for substitution, though. It's going to be a little bit easier to substitute this in. So I'm going to take this b, and up here I'm going to replace it with 4a. So I'm going to go ahead and do that right now. So I'm going to get 4a minus 2b's. That's going to equal -4. So I'm going to end up here with, I believe, -8. So 4a minus 8a is -4a equals -4. So a is going to equal 1. And if a equals 1, plug that in, you're going to get b to equal 4. So now a is 1, went up here, plugged it back in, got b is 4. All right, so that's how to do these problems. Make sure you check for the continuous, and then you actually find the derivative, And then the derivative itself is also continuous. That's why you're going to set those two equal to each other. So we have the graph of a positive function, and then we're going to sketch, or sorry, not positive, position function, and we're going to sketch the velocity. So here's a known little fact, is if the position is f of x, the velocity is the rate of change of the position. So this would be f prime of x. So all I want right now to sketch the velocity is to find the slope of the position. So these will all look like line segments. So I need to find the slope of this segment, slope of this next segment, which I know is 0 because it's horizontal, and then the slope of that last one. All right, so the slope of the first one, if I rise 1, 2, 3, 4, 5, 6, and run 1, 2, 3, 4, it's 6 over 4 is the slope, which is 3/2. And then I'm going to have to do this one, rise 1 over 2. So this one's just a 1/2. So when I go to sketch this now, I'm going to have to sketch, well, first off as well, when I go to sketch this, this is not differentiable right here because that's a corner. And it's not differentiable there because that's also a corner. And it's actually not differentiable at the endpoints either. So those are going to be holes. So I'm going to sketch a line segment with a height of 3/2, which is right here. And I'm going to have holes at the endpoints because it's not differentiable. So I'm going to sketch that all the way through 1, 2, 3, 4. So 1, 2, 3, 4. Okay. And then for the next 1, 2, 3 boxes, I'm at 0. And again, I'm using holes because it's not differentiable at these corners or at these endpoints. And then the next one's going to be at 1/2, kind of squeezing it on in there, but doing the best that I can do right there. Okay. So again, these are all slopes. All right. Last question. It's going to be a little bit on the confusing side. Just warning you for the immediate, and then I'll try to clarify it from there. Real quick, I'm going to make this color-coded. I know yours is color-coded. I don't remember exactly how the colored version is, so I'm just going to trace with what I got. So I'm sure this is not matching up with your colors. If you printed out the notes in, of course, that's running out. If you print out your notes in color, it's good enough right there. So we have blue, we have green, and then we have gray. All right, so for these problems to figure out which one's which, the easiest thing to do is to find a 0 and then find some type of horizontal tangent that matches up with it. Because if we find a 0 and we find a horizontal tangent, well, then that 0 is the derivative of the horizontal tangent. You'll see what I mean here in a second. So I have a 0 right here, and it matches up with the horizontal tangent right there. Okay, what that's going to tell me is that green is the derivative of blue. Okay, so is green the first derivative or the second derivative? I don't know that much yet, but I do know that green is either the first or the second. And as I go through, okay, I see another 0 right here, but I don't see any matching horizontal tangents. Okay, so that's actually going to tell me right there that this is actually the original function. Okay, because there are no horizontal tangents that go along with that. But I'll move a little further and use that same strategy that I talked about earlier. Here's blue being a 0 now, and it's got a horizontal tangent right down there. So now blue is the derivative of gray, and green is the derivative of blue. So this is what it tells me, that gray is the original. So gray is the original. That blue is the derivative, first derivative. And now green is the second derivative. writing that the best I can. It's kind of really faded. My green here ain't working out for me so well, but that's the second derivative. Okay. So I kind of said that it's going to take a little bit of practice to notice these. What I always do is I always look for my original function. And you can find that by when it hits a 0, there's not necessarily going to be any tangents that go with it. That's how I know that what my original is. Okay. So there is the second day of basic derivatives. A little more application and seeing what the heck we're really talking about here. And that's it.